Does this work? Yes? The mic?
Oh, yes.
Yes. Okay. Okay, so well, I think we should start anyway. So I wrote down so last time I treated in much details Minkowski space, and the point was to arrive at this definition, which I rewrote, but now in abstract term for a generic asymptotically flat manifold. So yeah. Here, yeah, we have discussed this, so let me not go. So yeah, so maybe the only point which is new, as opposed to last time. So Minkowski space obviously is flat, but asymptotically flat spacetimes are only Einsteins. So there is you have a constraint on the curvature, and so in practice, and what you need, so if you do pure gravity, there is just no T mu nu, no energy momentum tensor. If you want to add some matter, then to get something asymptotically flat, you will need to ask some sort of fall-off on this energy momentum tensor, which is the natural fall-off that you will have for radiative field. If you're having a scalar field or any type of matter which is the solution that you have in mind, they will give you energy momentum tensor of this type. So what I want to do today is spend a bit of time. Please, yeah.
The final definition.
Yeah, this is the final definition. It's not like this.
What about the size of this horizon?
Right.
It should be that we should be able to live forever when we are there. Observer time should not stop suddenly.
Yeah. So you could add. Yeah, you could add completeness. Sometimes also you want to add constraint on the topology of the boundary, like S2 times R. Actually, maybe I mean, sometimes people derive the topology from the field equations. I've seen people claim, but I'm not sure what are the underlying assumptions. So yeah, maybe you want to add explicitly the topology is S2 times R, that you have two boundaries. Maybe you want to add indeed completeness of the boundary, but this would exclude black holes. But you can do this.
No, not to exclude black holes, to actually make black holes really good, to distinguish between black hole and just a hole in space-time. However,
right.
A hole which we didn't manage to see because our time.
So what would you like to add as part of the definition?
Yeah, so usually you introduce affine parameter along null generators of scry, and you require that this null parameter goes from minus infinity to plus infinity.
Right. So yeah, if you want, you could add this as well.
On each branch.
Yeah. So you could add this as part of the definition. For what I'm going to derive, this is some sort of global feature that you might want. For what I'm going to derive, they are going to be very local. So yeah, I would not miss this, but yeah, you could do this. Another thing you might be worried of is something that I've been asked I had a few questions on Tuesday about space-like infinity. You might be worried, especially with this idea of flat holography, that there is a global BMS group. Maybe you want some sort of relationship between scry plus and scry minus. So you might be worried about what's the behavior of the fields as you go to space-like infinity. And again, as I was asked yesterday on Tuesday, there is nothing in this definition a priori that tells you anything about the behavior at space-like infinity. So you might want to add something about the behavior at space-like infinity. But of course, I mean, the difficulty here is that you can put anything in your definition. The question is, do you have non-trivial solutions? So at least here, and even if we ask that the boundary is complete and we have two of them, we know that there are vast class of solutions, so they are good enough definitions. The question is, to which extent can you require the behavior at space-like infinity? How much does this constraint dynamics? I think is still somewhat, to a big extent, an open question. So yes, is there any other comment on this definition? Yes?
So the follow-up of the energy momentum tensor follows from like finite energy conditions, or is it just something?
Yeah, typically if you take your field, which are, you expand them in Fourier modes and everything, they would have this fall-off behavior. Yeah, this fall-off will ensure finite energy condition and this sort of things. Yeah. Okay. So again, one thing that I want to emphasize, hopefully in the lecture, is that The definition is very simple, and yet it leads to quite a lot of nice properties that you might want inside of your spacetime. So that's why it was a good definition. I would try to get to the point that in particular it implies BMS group, but also Einstein Sachs spilling. I'm not sure to which extent I will be able to discuss this. But yeah, so let me say it now, unless I don't have time to get through the nitty-gritty details here. This definition, which looks very, very different from Sachs' initial ideas about how the Weil tensor behave, this implies Sachs spilling. I'll come back on this later on. Okay, so something you should keep in mind when you see this definition is that there is nothing unique about the scalar field and the metric. They are really defined. This is a conformal compactification. So really, this guy, they are defined up to rescaling. So in particular, the normal at the boundary, so which is this G mu omega G nu. And also the metric at the boundary, which I'm going to call H. I call G. This is the restriction of the metric at the boundary. Those guys are also defined up to multiplication like this. Well, I mean, let me write this. Okay, so also, just for future convenience, I'm going to use x mu as coordinate on spacetime, and xa, so these are xa as coordinates along scry. So this will be hkb, dxa, dxb, xa, coordinates on scry. Good, and these guys are only defined up to n h goes to lambda minus 1, 0 of xa, and lambda 0 squared h, and lambda 0 is of little xa is just the restriction of this lambda x at the boundary. Okay. So now we want to discuss a bit of the properties of this object, of this normal. What can we deduce on this structure from these assumptions? So so the normal is null, so n squared, so n mu g mu restricted at scry equals 0. So the normal is null at scry. So in particular, what this implies is that you can check that it implies that the normal is, it annihilates the derivative of omega, which means that the normal is tangent to scry, so it's a null normal. We'll see that we have this implication. So I'm going to write n as n little a d of dxa. This is really a vector field inside the boundary. And the induced metric is degenerate. Yeah, so this metric. Which I'm going to call induced metric. Wow. So it's degenerate, so we have this is null geometry. And they relate to the vector field as follows. So when we contract the vector field in the metric, we get 0, but also, not only this, but also the Lie derivative of the boundary metric in the h direction, in fact, is proportional to h. Okay, so if you want degenerate of signature, 0 plus plus. So it's same feature as that scry. We had this, so let me, this is what then I will want to call the universal structure of the infinity. Let me write it here. And then I will take a bit of time to see how these features, they follow from the definition. Let me just write this definition. So from this, I'm taking this from error 77. And many people are following this terminology. So this is the universal structure of the infinity. This is this pair of vector field and metric. They are conformal, so they are only defined up to this. And they satisfy these two conditions that I wrote up there. So one is in the kernel of the other, and the E derivative is proportional to HAB. Yeah, so this is. So we have this. Sometimes, yeah. And as I started to explain last time, sometimes the literature you will always find, you will also find the idea that this is also known as Carolian geometry, because you can obtain this from a Carolian contraction. And yeah, so you can see there is this Carolian contraction. They are discussed in Gibbons, Duval, Horvath, Senk. If you want to read a bit about this. So I want to derive for you these properties, and you'll see that these are, it's a nice exercise in conformal geometry. Well, in you'll see that how this works. Any question about this? No? Well, hopefully now it all looks very similar to the Minkowski space situation, so nothing is surprising at all. So how does the proof work? It really has to do with this specific behavior in 1 over omega squared. So let me do proof. So you have to start with the shorthand tensor. So there is this definition, recall that the shorthand tensor or Scartan tensor is the following object. So P mu nu. So this is definition of Scartan tensor. This is some version of the Ricci tensor, but which is trace corrected, subtracting some version of the scalar curvature. The reason why this object is of interest in conformal geometry is that it transforms nicely under conformal geometry, under conformal rescalings. I'm going to write P tilde is P of G tilde, and P, which is 1 over omega squared G, and P means Scartan tensor of G. Right, this is my notation. And we have, so it's classical, this object has a classical transformation rule. So we have P tilde mu nu with this relationship here. It relates like this to the, so this is the physical Scartan tensor, and I'm computing it in terms of the unphysical one, P mu nu minus, it works like this, mu epsilon nu plus epsilon nu minus 1/2 epsilon rho g mu nu, where this epsilon is defined as a function of the rescaling. This is minus omega nabla omega. So you just go through the computation and you find more explicitly that this has this form. Okay. So now what can we say about this expression? So this is essentially the Ricci tensor of the physical metric, but therefore it has to satisfy Einstein's equation, so it goes to 0 very quickly. So this object on this side must essentially be, is going to 0 as we're reaching to the boundary. On that side, this object is the unphysical metric. It's finite at the boundary. So this object is finite. This object, they both are non-zero. And therefore, and this is finite. So these guys, they are divergent, so they cannot be here. So they must be suppressed. So we have already found an equation. So Einstein equation on G tilde nu means that this P tilde nu is finite. In fact, 0 as omega goes to 0, and thus this term cannot be here. So this much vanishes, but what is this? Well, this is, in fact, so at scry. So 0, when evaluated at scry, this must be 0, but this is precisely the norm of the metric, of the vector field. Equals 0. Okay, so this is already giving the first point, then the normal must be null. Immediately follows from the fact that this must be finite. Good. What about the second term? So this term also is divergent, so also should be 0. Let me not write it. So it should be, where is it? Yeah. So 2 derivative of omega evaluated at scry also should be 0. Ah, yes, but this term could be here. So in fact, we don't really know what's going on here. I don't even want to compute. I know, but I know it can only be proportional to the metric. So what this tells me is that this, in fact, this object should be at scry, should be proportional to the metric at scry. Okay. But what can we say from this? So this again is the normal. So this is really the same as saying that this object is proportional to the metric at scry. Okay, but now if I really, but this can be rewritten by saying that the Lie derivative of the metric in the normal direction, because I can symmetrize. I can symmetrize for free because we can already see here that this is symmetric. So this is the same as this guy, which is the Lie derivative of the metric. So the Lie derivative of the metric at scry is proportional to G mu nu. So here at that level, I'm really working still in the space-time indices, but you can easily convince yourself that if you reduce it along scry, you get this second property. So okay, so we see that these two first items which are the definitions of this universal structure that really just follow from the fact that this object should be finite at scry. I'm even not using completely the full assumptions that are there. It's really the leading, it's really the requirement that this guy cannot diverge. Okay. Is there any question about the proof? It's a nice exercise. Good. So now we saw that this definition implies the existence of this structure at scry. We're going to derive a bunch of properties which are associated with this object. Yeah. What can I do? So we are going now. We are going to write this down. Because of all these nice properties, this means that we can really write this object in very simple. We can choose coordinates which are very well adapted and which make all this structure very trivial. So let's do this. So adapted coordinate system. Okay, yeah, so why is it universal? So the structure is universal because of the following. Because, well, in fact, it's always the same proposition. There are no degrees of freedom, in which sense one can always choose U, Z, Z bar coordinates on scry. And you see, so these are all very local statements. There is nothing about the topology or whatever that I'm using at this stage. This is all very elementary at this stage. So you can choose the coordinates and the Weil freedom. So you can do these rescalings. And H goes to lambda minus 1, 0, and lambda squared H. To take following, well, N is just going to be D over du, and H is just, so here, 0 du squared. I'm writing 0 to re-emphasize that it's a degenerate metric, plus 4 dz bar divided by 1 plus modulo squared z squared. And this is the round sphere metric. And this was exactly, I think I forgot to write at the end of the last lecture what was the structure at scry in terms of the BMS coordinates, but this would have been the answer. So this has the same form as for Minkowski space. So it's universal in the sense that it's always the same. There is no degrees of freedom. You can always choose a coordinate system, do a Weil rescaling, and there is only one structure at scry. There is no degrees of freedom here, no gravitation here. It's always the same object. So I'm wondering if I have time to do the proof. I think I will let you as an exercise to do this proof. So the proof is in the notes. It's a little exercise. It's not much. It really has to do with the fact that, okay, what's the essence here? I mean, what's really make it trivial is the fact that this is conformal geometry, but conformal geometry in two dimension is completely trivial. There is no local degrees of freedom in two-dimensional conformal geometry. You can always choose it in 2B whatever nice representative you want. Now, Any question on this aspect? No? Good. So now from this we can obtain the BMS group. So we have this structure at Scry. It's universal in the sense that whatever you do, whatever crazy spacetimes you want to consider, it's always going to be the same in a sense. So we can look for the group of symmetry, the group of automorphism of this. And this turns out to be precisely the group of symmetry that we like, the EMS group. So now I'm working in this adapted coordinate system. And this is already a result that you can find very clearly. Well, at least this is the oldest place where I know this is very clearly stated in Gerard. Let's review. So probably already at the time it was clear for most people. So the Lie algebra of symmetry. Of this universal structure. So what does that mean? Well, this means that I take a vector field, which is going to be x, and I want to act on this structure. So I act with the Lie derivative on my vector field, NA, and I'm going to act with my vector field on the metric as well, HB. What do I obtain? So one answer could be I want to obtain 0, but you don't quite want to obtain 0 because this object is only defined up to multiplication. So really what you want is you want something which is there is some function, some free function in front. So this is the definition of infinitesimal symmetry, right? This is the definition for some alpha. And this is generated by vector field x with the following form. So we have two free functions, something which I'm going to call zeta of z and z bar, plus there is this divergent term. So we're here. We have the following. We have free functions. So zeta is a function on the sphere. And this chi of z. Well, then sort of this depends. So it's a conformal vector field. on, and then here, so this is going to be S2, so therefore I will just, it's just show new polynomial, A plus BZ plus C Z squared. Of course, if you sort of don't really care about the topology, you would get any conformal transformation and the full with algebra. What is more, the Lie algebra is isomorphic to, well, the Lie algebra of SO31 acting on function on of the sphere. And here you have to yeah, this is the BMS Lie algebra. But here you have to be careful when you write those things, exactly what is the action here. So you have to remember that here the action of SO31 is, well, so SO31 acts here, acts as on conformal primary of weight minus 1. So it's a very any question on this? No. So it's a very straightforward, and I think first time I saw it, very impressive results. That's such that the BMS group really just is the group of orthomorphism of this structure, which is very weak. It's really just coming from the very, as we saw, we're not even using this. You're really using the fact that the physical Scartan tensor is not blowing up. So maybe, yeah, a bit of what is going on, a bit of the proof. So in this coordinate system, the proof is just a direct computation. Just compute this Lie derivative and see what it imposes. But I want to write down the Lie algebra just because I have to at some point write it down, this Lie algebra. Okay, so proof is that the expression for x is given by a direct computation. In the adapted coordinates. So, and then for the Lie algebra, if we note, so let me write x of zeta, or x of psi, as, this is psi z bar du, and y of chi as being this u over 2 nabla z chi z plus nabla c bar chi z bar du plus chi z plus chi bar dz bar. Then it's immediate that these objects, so if I have two functions, xi1, xi2, they commute because they do not depend on u. So we have an abelian subalgebra which is isomorphic to function, which is the abelian the algebra of function on the sphere. The y's between themselves, they are the Lie algebra of function on the sphere. So, well, no, not this. This gives you y of chi1 d z chi2 minus chi2 d chi1. So this is, you get the Lie algebra of SO31. And finally, the most interesting bracket is when you act with the SO31 on the super translation. You obtain y of z tilde, where precisely this psi tilde is chi dz plus chi bar z bar acting on zeta plus or minus 1/2 t and yeah. And this is this conformal primary transformation rules that I was talking about. Okay. What did I do? Yeah, x. Yeah, thank you. Indeed, so we get another super translation Spacetime. So yeah, rotations act on the space of functions, and they act, in fact, on these functions. They are conformal primaries with a fixed weight. So a few remarks. So I imagine that if you come to this workshop, you have somewhat of an idea of what the BMS group is, but let me discuss the structure anyway. So this should be thought as an infinite dimensional extension of the Poincare group. Poincare group would be SO31 acting on R4, but here, instead of having R4, we have an infinite dimensional space of function on the sphere, which are, so this are your usual rotations. Maybe if you want to relax the topology, you could have any conformal transformation on a local open set. These are an infinite generalization of translation. Instead of having R4, you have function on the sphere, infinite dimensional. You should ask yourself, where does R4 sit inside the space of function on the sphere? There are several ways of thinking about this problem. One way to see R4 here is to look for the lowest order spherical harmonics. So spherical harmonics 0 and 1. This gives you three functions, and these are R4. And naturally, there are 4 functions on the spheres. Another one that I like, then really a matter of taste, is that if you have a metric like this, you can ask yourself, if I multiply this metric by a function on the sphere, does this new metric has constant scalar curvature? Is it another sphere? In general, not. But if you take this metric, multiply by this, and look for functions such that the metric is again another sphere function, you will get a 4-parameter family of functions. These are the same R4. It's another way of thinking of R4 as inside the space of function on the sphere. Is there any question on this? Yes? No? It's fine. And we see that here the reason why the BMS group appears is the fact that this geometry is very weak. This structure here, well, is degenerate. So there is, maybe I should give some geometrical insight about what's going on here. So scry is fibered by these u coordinates. So the picture you should have in mind is that you have this fiber here, each of the fiber is constant z equal constant. While the u's, they are sectioned like this. So you see there are some spheres, some cuts, as one says. It's a fiber bundle, so you can always quotient by the space of line and get just the sphere on the quotient, and then we have this metric on the quotient. And the fact that there is this quotient in the total space of Scry, well, from the algebra of symmetry, you obtain it by this semi-direct product. So the semi-direct product structure in the symmetry of algebra, it's resonates with the fact that the geometry of Scry is a fiber bundle, because you can quotient by lines, and here you can quotient by super translation and obtain the group. The fact that this is infinite dimensional is due to the fact that this translation, they really translates you along each of the fibers. And each of the fibers, they absolutely don't talk to each other. There is no structure relating this fiber to this other, so it's just all you have is there is no way to reduce it to something smaller. Okay, that's more probably all I wanted to say here. Yes?
Is there a weaker definition of universal structures such that the symmetry algebra now includes super rotations?
Yes, the super rotation is really, well, I mean, depends what you mean by super rotation, but if you mean conformal holomorphic, any holomorphic transformation of the sphere, this is, it's just a question of topology. So this definition, naively, if you work on some local open sets, you would not get SO31, you would just get any holomorphic transformation. Here already, okay, maybe I should say this. Here already, when I say this, I suppose that Scry really is S2 times R. This really has to do with the topology of the manifold. Okay? If you don't want, if you want something more, sometimes people want not even super rotation, but I never remember the word. There's this any diffeomorphism of the sphere. Well, you can just suppose that you don't care about the metric. You just forget about this metric here. Just forget about the metric. You just keep the vector field. But now, to get the right, you would get here any diffeomorphism. To get the right action here, you will have to keep in mind that this vector field should be weighted in a sense. Okay, so if you want, if you forget about the metric, there should be some sort of way to remember that still the vector field has some weight. It transforms in a particular way. Okay. Okay. So now I'm going to discuss peeling. Hopefully, I will have time to have a nice discussion on that. If there is any more discussion. So tomorrow, I will construct. I will discuss BMS coordinate system, and we'll find again the same group, probably in the construction that you've seen before, that you are bound to see many times. That you can also think of this as being Lie algebra as asymptotic symmetries. Here they are very asymptotic in the sense that we see them. They are the symmetries of the structure induced at Scry. I'm presenting this in this way, also perhaps probably with this idea that if you are really taking seriously this holographic idea, well, this is the group of symmetry of the boundary itself. But also tomorrow we'll see that's also the group of asymptotic symmetries of your spacetimes. Okay. So all this is essentially local in nature and quite a straightforward definition, corollary of the Penrose definition. There is some fact which is a lot less obvious, which is Penrose peeling. To discuss this, I need to remind you that the Weil tensor is conformal invariant. So the Weil tensor is it's conformal invariant really in the most obvious sense you could have. So it's really that the Weil tensor mu nu rho sigma of the physical metric really is the same as the Weil tensor of the n-physical metric really is the same object. And for this to be genuinely conformal invariant, it's very important that this indices is upstairs. Otherwise, you have some rescaling. So this is some sort of things that I will need. So yeah, it's a classical result. Just prove it if you want by direct computation. Now, here is a nice theorem due to Penrose, 1963. So assuming, so here you really need to assume that scry is S2 times R. So topology of the sphere is really important. And I'm going to say something which I've been asked, I think, yesterday on Tuesday about how much of differentiability you want to ask. So here, and G mu nu is at least C4. So for these two hold, it's really important that the metric is 4th time differentiable. Then the Weil tensor evaluated at scry of the, so this is the Weil of the n-physical metric, but by conformal invariance, it's also the Weil of the physical metric. This is 0. Yeah, this is what we call, this is, yeah, I'm going to call this Penrose spinning. I think everybody would understand you if you say that this is Penrose spinning. I'm not going to prove this. It's not, well, there are different ways of proving this, but what's crucial is that to prove this, you need both topology and differentiability. So yeah, why am I talking about this differentiability thing? So as you will, okay, so I should already say something as in why this is interesting. So one thing that is not obvious from the definition, but which I will have to, I probably can sketch the definition, is that, in fact, Penrose spinning this implies Sachs spinning in the sense that I said last time. So in other terms, by this, what I mean is you take any null geodesic congruence going to scry, and you will find that it has to satisfy Sachs spinning. It's coming from the fact that this is satisfied. So why? So this is what the thing that I started from is. It's really not obvious from this definition that in fact Sachs' initial intuition about how the Weil should behave asymptotically follows, but it just turns out that topology imposes this, which in turn implies Sachs spinning. So in the first lecture, I wanted to talk about Sachs spinning because this is sort of folklore. This was very important for the historical construction of the definition, but also because nowadays you will very frequently people ask, well, does your solution satisfy the pinning or not? What's going on? And one thing, the reason why people are still interested in this, despite the fact that nowadays we are not really thinking, most people are not thinking of Sachs spinning as being some very deep physical significance. The reason still why it's an interesting notion is because of this theorem, because you see that if your conformal compactification is smooth enough, then you do have Sachs spinning. So for most people, when they say, do you have pinning, what they have in mind is, to which extent do you have logs? To which extent do you have lack of differentiability at scry? So, and you would typically hear mathematicians saying, well, if we construct this and this type of solution with a stability result or whatever. However, it lacks spilling, or maybe it has only this component of the Weil tensor which is spilling. And what they will try to convey by saying this is to which extent their solution fails to be C infinity as they describe. This is what people have in mind when thinking about the pinning, is that nowadays, really the peeling is a smoking gun. Peeling or not peeling is a smoking gun for lack of differentiability at Scri. And not so much as a very deep physically significant stuff. Yeah, I'm going to, before I sketch the proof, there is a remark I need to make that sort of makes sense of this.
Hi, Yannick.
Yeah.
I have a dumb question.
Yeah.
To what extent is the converse of this?
You mean if this is 0, then this implies some level of differentiability?
Can you deduce something about the topology of Scri?
No, I don't think so. I don't think so.
I don't think.
No, I don't think so. No, I don't think so. Because so one way I know how to prove this, which is very pragmatic, we're really hands-on, is you run through the BMS expansion. There is this D coefficient that appears. So I will write down this tomorrow. There is a D coefficient that appears after the asymptotic shear. This D coefficient should appear in the Weil tensor, in the leading Weil tensor. So it should appear here and violate peelings, but it cannot because if it needs to satisfy some PDE to prevent the log term to appear. Now with this PDE, which is preventing the log, and the topology, it has to be 0. And this is why it works. So I think this guy could really be 0, and still you could have a log at some other terms that would be fine. I would imagine this. Yeah, let me discuss a bit of Newman-Penrose before anyway, to write to sketch the proof, I will need a bit of a Newman-Penrose coefficient. So let me, yeah. Comment on this. Because as opposed to the previous, the first lecture, so in the first lecture, what we are doing is that we are choosing a null geodesic congruence, and we are constructing the Newman-Penrose coefficient as some sort of invariant object for the null geodesic congruence. Here, a priori, we don't have any null geodesic congruence. You can choose one if you like, but a priori, there's no preferred choice. But on the other side, we have this Scri. We have this Scri, and along Scri, you have n mu. So now you can do the following. You can construct a null tetrade by taking m and m bar inside Scri. So really, you should think that this is du, this is dz, this is dz bar. And then from this, you have an outward pointing L mu, which is your dr. And this dr is pointing towards your null geodesic congruence, or the other way around, depends on. So this is Scri. This your null geodesic congruence going in here. Or maybe maybe it's reaching Scri, then it goes in the other side. So it's the same situation, but the status of L and L is reversed. Because whenever you have a null, in the null geodesic congruence, the starting point was L, and therefore, so for the null geodesic congruence, it seems that the main object was psi0, and psi0 was Weil, mu, rho, sigma, where I would plug the L, and mu, m, mu, L, rho, m, sigma. So this was for the null geodesic congruence because L is the invariant object, but this is here. L is massively undetermined because there is no precise way of choosing this disease. They are not unique, but now we have another, now it's psi4, which is you take Weil, mu, rho, sigma, and you plug n mu, n mu, n rho, m, sigma. This object for Scri is the invariant object. And indeed, because n is unique, well, and m is not unique, but it's unique up to addition of n, and therefore it doesn't show up. So this guy is invariant. This is the gravitational. So this is an invariant of the geometry along Scri. This is the gravitational. Sometimes, well, Penrose refers to this as the gravitational field. And this was also in Sachs peelings. This was the object that was falling off the slowest. Right. So just you have to realize that as opposed to when you're thinking of scry, as opposed to this nudge of the congruence picture from the first lecture, I want to insist that the role of n and L are inverted, so things go in the other order. So if psi 0 is 0, then psi 3 is the invariant. If psi 3 and psi 0 and if psi 4 and psi 3 are invariant, then psi 2 is the invariant guy, etc., etc., etc. Okay, maybe I should also, there are many things I could say, but okay, yes, and here, okay, here I already made some mistakes. So this looks very nice formula, but it's meaningless because it's 0 by tensor vanishes. So if you want to get a non-trivial object, so this is what really is psi 0, 4, you need to multiply this by r. Now this object naively is divergent, but by Penrose splitting it's not, and you restrict it to scry, and you get a finite piece, which is the psi 0, 4. And let me, I have 5 minutes to try to give you the insight why Penrose splitting implies Sachs splitting. So first of all, you see here, I purposely used object without any tildes to emphasize the fact that this null tetrade really, so everywhere I'm going to use this notation that n mu, m mu, m bar mu, l mu is null tetrade for the unphysical metric, for G mu nu. So now I want to construct a tetrade tilde mu, m bar tilde mu, l tilde mu for the physical metric, G tilde mu nu, but this one diverges as 1 over omega squared. And we need to see what are the implications. And of course, why do you do this? Well, of course, Sachs splitting, in the way that it was, that I discussed this in the first lecture, is something physical. So it's something that you should compute in terms of the physical Newman-Penrose, well, I mean, the physical null tetrade. So yes, let me, but for this, for example, psi 0, which was the, let me do psi 0. So psi 0, which was with a tilde. Let me emphasize that these are really the physical Newman-Penrose coefficient. This should be while tildes mu rho sigma L tilde mu m tilde mu L tilde rho m sigma tildes. And now we want to understand how does this go to 0 as r goes to 0. So we know already that this guy goes to 0. So naively at least, this is going to go like 1 over r. So if you want to know how this behaves in terms of r, we need to know how this tetrade behaves asymptotically. But what do we know? Well, we know that it has to be a null tetrade. So we know that, let me write it somewhere else. So the behavior of this unphysical null tetrade is directly going to follow from the definition. So recall that n, so the physical one as well as the unphysical one, this is the same thing because this is the sort of invariant geometrical object as well, so it doesn't change. But we know that by definition we must have that n mu L tilde mu G tilde mu nu equal -1. But this goes as 1 over, well, this goes as r squared. This is divergent with r squared. It goes as 1 over omega squared. And therefore, this should go like r minus 2. So thus, in fact, L tilde mu, it should go as r minus 2 times L mu, where L mu is going to be the unphysical null tetrade. But also, we know that m tilde nu m bar tilde nu g tilde mu equal 1. But again, this object goes like r squared. They should have the same weight. So the only way is that this goes like r minus 1, and also this goes as r minus 1. And therefore, we found the relationship between the null tetrade, the physical null tetrade, and the physical and the unphysical null tetrade. So these guys, they are finite at scry, and these ones, they are not. They go to 0, but with a prescribed fall-off, which is given, which is constrained by their definition. And therefore, what did we find? Well, this goes like r 1 over r squared. This goes as well. Anyway, this is 1 over r. This is 1 over r squared. This is 1 over r. This is 1 over r. This is 1 over r squared. And therefore, we add up 2, 3, 4, 5, 6. What's going on? Yes. Yeah, this is not going. So this is one way of doing. This is one easy way of doing a mistake in this computation. So this guy is going to 0, but I lift up the indices. So let me write this explicitly. So this one is going like 1 over r, but what you need, let me write alpha, you lower down the indices with the physical metric, and this goes like r squared. So now I should get the right answer. So this compensates 1, yeah, I get 5. So 2, 3, 4, 5, r minus 5, which was indeed Sachs' peeling property. You can run this argument for all the other Newman-Penrose coefficients, the physical ones, with the physical. Sachs peeling is supposed to be physical, so you should compute it with the physical tetrade, and therefore it will give you these different fall-offs. And you see, the magic here is really has to do with this feature, is that the Weil tensor itself just goes to 0, and the subleading terms, they are all at the same order. So all these coefficients, the Newman-Penrose coefficients, they all appear at the same order, subleading, in the physical or unphysical Weil tensor. What makes them peel is the fact that you're expressing the coordinates into the physical null tetrade, which has this particular behavior, and this is what makes the Weil tensor peels. All right? That's how, this is how these things which looks like very local, just one, just saying that Weil tensor vanishes at scry gives you the peeling. And I think that's all I wanted to say for today. Let me check. Yep, thank you. Any question on this? No? Well, okay. Thanks a lot. And, so see you at Sabrina's lecture. Yeah.